The Webb glance is such a long way out that it's catching light that has been voyaging for over 13 billion years. Yet the universe has been extending, and thus the light has been extending for the most distant worlds. We're reminiscing almost back to the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we allude to as the singularity. The Big Bang hypothesis may be interpreted in this manner at this time. Anyway, the James Webb Space Telescope, JWST, has revealed significant mysteries about the birth and development of the universe, leaving us dumbfounded. According to renowned physicist Brian Cox, the significant discoveries made by the JWST may actually alter our comprehension of the universe as a whole. Join us as we dive into these new heavenly discoveries that promise to change our comprehension. The James Webb Space Telescope, named after the recognized NASA executive James E. Webb, remains a wonder in current galactic investigation. This telescope represents a huge mechanical leap forward from its ancestor, the Hubble Space Telescope. Coming about because of a cooperative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the abilities of its herald. It makes use of cutting-edge technology and has a design that is better suited to focusing on the universe in incredible detail. Not at all like the Hubble, the JWST conveys clear and sharp pictures of far-off heavenly bodies, working primarily in the infrared range. This interesting component permits it to infiltrate astronomical residue and catch divine items that were beforehand stowed away from our view. With its giant 6.5-meter primary mirror made out of 18 hexagonal sections, the JWST diminishes the Hubble's reflector size. Situated roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it circles the Sun in a state of harmony with Earth, ensuring a steady and continuous view of the universe while looking into the far-off corners of the universe. It involves exploring light years, but it also involves a type of time travel. The JWST uses infrared instruments to notice heavenly objects and events going back billions of years. The light emitted by these objects, because of the expanding universe, goes through redshift, moving from the apparent range to the infrared frequency or longer. Luckily, the JWST can identify infrared light radiated by heavenly bodies at extreme distances, empowering researchers to study the introduction of stars, investigate galaxy development, and examine exoplanet atmospheres. Its latest historic discovery involves identifying an incomprehensible mass of cosmic systems at the edge of the discernible universe. Our fundamental cosmological assumptions need to be rethought in light of this finding, which casts doubt on the veracity of the theory of how things came into existence. To better understand how we arrived at this point, we should take a short excursion through the history of space investigation. Early civilizations, like the Greeks and Chinese, laid the foundation for understanding planetary movement by noticing divine bodies. Newton's regulations in the 17th century gave a hypothetical structure for space travel. In the mid-20th century, Edwin Hubble, an influential astronomer, made historic revelations in cosmology and observational space science. His observation uncovered that far-off nebulae were isolated worlds long past the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law, established by him, showed that galaxies farther away were moving away at higher rates, giving proof of the expansion of the universe. The post-World War II history of space exploration marked the beginning of the space race, with the Soviet Union's Sputnik in 1957 as the first artificial satellite in orbit. The orbital journey of Yuri Gagarin in 1961 and the 1969 landing of Apollo 11 on the Moon were significant achievements. Fast forward to 1990, when the Hubble Space Telescope was launched, giving exceptional clarity and stunning insights into the universe. The journey from ancient observations to the technological wonders of the James Webb Space Telescope showcases the constant development of how we might interpret the universe. It uncovered the boundlessness of space and changed fundamental thoughts in astronomy. Take the Hubble Space Telescope, HST, for instance. It snapped the famous Pillars of Creation image in the Eagle Nebula, revealing a star nursery formed by massive columns of gas and dust. Another significant accomplishment was the Hubble Deep Field, capturing a huge number of galaxies in a seemingly void patch of space. The HST also dove into exoplanet atmospheres, pinpointing components like water and organic molecules in distant worlds, alluding to the possibility of habitable zones beyond our solar system. Following the development of the closest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These achievements cemented the Hubble Space Telescope's legacy as a foundation of modern cosmology, dazzling the world with its incredible discoveries. Its replacement, the James Webb Space Telescope, was launched to expand on the technological advancements and lessons learned from a model of our understanding of the universe's origin. Today, this is explained by the prevailing theory of the universe's origin around 13.8 billion years ago. The universe began as a very hot and dense singularity, rapidly expanding to include matter, energy, and basic forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the various structures observed today. The Big Bang theory also explains cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Despite being widely accepted, the Big Bang theory faced skepticism and challenges in its early days. Alternative models, like the steady-state theory, proposed a universe without a specific beginning, and concerns about proof supporting the initial singularity expansion and observed anomalies arose. The majority of these objections were addressed over time, and the 1965 discovery of cosmic microwave background radiation, which corresponded to Big Bang predictions, provided a significant piece of evidence. Space missions like COBE and WMAP, alongside technological advancements, further supported the theory. The theoretical predictions and the precise measurements of the cosmic microwave background radiation were remarkably compatible. Enter the James Webb Space Telescope, equipped with advanced infrared instruments that can look through cosmic dust. The JWST, working primarily in the infrared range, captures the oldest light in the universe and observes objects formed shortly after the Big Bang. Its infrared abilities allow it to concentrate on star-forming regions, celestial nurseries, and the formation of stars hidden from optical telescopes. Infrared light, with longer wavelengths compared to visible light, can penetrate interstellar dust, overcoming a limitation of the Hubble Space Telescope. The JWST can observe cooler objects emitting mainly in infrared, making it ideal for investigating phenomena like brown dwarfs, exoplanets, and faraway galaxies. The James Webb Space Telescope, JWST, excels in detecting cosmic signals. As celestial bodies move away, their emitted light waves get stretched, causing a shift toward longer wavelengths, redshift. The JWST's infrared capabilities can detect these redshifted signals, capturing light from the early universe and offering insights into its formation and evolution. Energetic events like black hole mergers or new star births primarily emit in the infrared range, further expanding the JWST's investigative capabilities. The telescope can explore phenomena that would otherwise be hidden or invisible. The JWST supplements optical telescopes, like Hubble, by having enhanced sensitivity and the ability to detect infrared radiation. This ability allows it to peer further into space and dig deeper into astronomical history, revealing hidden astronomical wonders and providing a more comprehensive view of the universe's development. The JWST serves as our window into the earlier phases of cosmic evolution. Recently, it revealed something so astounding that it might prompt a reconsideration of the entire cosmological model of the universe. At the very edge of the observable universe, we have found galaxies with enormous masses. These ancient galaxies existed just a few 100 million years after the Big Bang, during the cosmic dawn. The puzzling part is that we're unsure about how such enormous structures formed so early in the universe's history. This discovery might lead us to reconsider our understanding of the formation and evolution of galaxies in the early universe. For understanding the mysteries surrounding the origins of the universe, it is essential to investigate early galaxies. The JWST can gain insights into how galaxies, stars, and planetary systems arose and evolved over billions of years. These observations also contribute to broader questions about the fundamental nature of the universe, including its composition, structure, and the forces governing its evolution. While the Hubble Space Telescope was groundbreaking for its time, it had limitations in observing the early universe. Its main limitation was its inability to effectively penetrate cosmic dust and detect the infrared light emitted by ancient galaxies. Older telescopes relied on visible and ultraviolet light observations, making it challenging to explore the early universe, where these wavelengths are absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope is a significant advancement in our understanding of galaxies in the early stages of the universe. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang. The JWST's infrared sensitivity and advanced imaging capabilities have revealed a plethora of ancient galaxies, providing remarkable clarity and detail for comprehending the evolution of the universe. Existing cosmological models have been shaken by preliminary JWST observations. The detailed data challenges several aspects of prevailing theories, prompting cosmologists to reconsider fundamental principles governing how we understand cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have sparked intense debates within the scientific community. JWST observations have revealed a larger number of galaxies in the early universe than anticipated by existing models, suggesting a more complex and rapid evolution process. Some observed early galaxies appear more developed than expected, challenging conventional models predicting slower development. The discovery of an unfathomable mass of galaxies challenges the assumed distribution and arrangement of large structures, revealing a more intricate and denser cosmic web than previously thought. These observations bring up fascinating inquiries and possibilities for further investigation. The existence of large structures challenges early models of cosmic structure formation, prompting researchers to refine models for a better explanation. Understanding how such vast structures gathered rapidly after the Big Bang presents a puzzle that requires an explanation that doesn't violate fundamental principles of cosmology. Significant disparities in the conditions of the early universe, compared to predictions based on existing models, have also been revealed. These differences could suggest previously unknown physical processes, unexpected conditions, or unidentified cosmic phenomena. In simple terms, these variations have prompted scientists to rethink and improve our models of the universe. For the time being, all we can say is that more research is needed to incorporate these surprising findings into a more complete understanding of the universe. Initial observations often provide exciting glimpses into the universe, but investigations sometimes reveal differences. For example, early observations may show specific properties or arrangements within distant galaxies that, upon closer examination, reveal fluctuations in their composition, structure, or evolutionary pathways. In conclusion, enormous phenomena are incredibly complex and require careful investigation for us to accurately understand their true nature. Spectroscopy, a method that helps unravel the properties and history of celestial objects, is an example. It involves analyzing the light emitted or absorbed by astronomical objects. By examining the properties of the light, spectroscopy provides detailed information about the chemical composition, temperature, density, and movement of celestial bodies. This analysis helps us understand the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations differed from later investigations. For instance, Initial observations of distant galaxies suggested a simple structure, primarily dominated by lighter elements like hydrogen and helium, in line with theoretical expectations. However, spectroscopic analysis using the JWST showed fascinating variations in elemental signatures, identifying heavier elements or compounds previously undetected or misunderstood in the early universe. This raises questions about how the early universe's chemical composition developed and spread over vast distances, as well as the mechanisms by which it did so. Similarly, initial assumptions about galaxies in the early universe were based on preliminary observations suggesting a relatively uniform pattern of development and organization. However, more detailed investigations by the JWST revealed a much more diverse and complex array of chemical compositions within these galaxies.